Okay, welcome guys. This is 4.5 optimization. So we will be optimizing problems. That means we will be figuring out an equation, all in terms of one variable, to maximize or minimize. So we already know how to do that because we've already been finding maximums and minimums. To find a maximum or minimum, we will take the derivative, set it equal to 0, and solve for x, or whatever variable we are dealing with. So that's what we're going to do here for these applications. So there are steps there to solving an optimization problem. 1, understand the problem. What formulas, what quantities, what equations do we need? Step 2, draw a diagram if you need it. Diagrams are always helpful. 3, introduce notation, assign a variable for the quantity to be optimized, and assign a variable for the unknown quantities. So we want to know what formulas should we use. 4, once we find the formula, we need to express it in terms of one variable. This is because when we take the derivative, we do not want an implicit derivative. We do not need a variable. We do not need an extra variable, right? We don't need an extra variable. That's it. So that's why it's best to have the function in terms of one variable. And once you have it in terms of one variable, then it will be okay. Take the derivative, set it equal to 0, solve for x. Okay, so those are steps to help you solve an optimization problem. And you may be asking, what is the difference between maximizing or minimizing a function? Well, it all is going to depend on the problem. It all is going to depend on what the problem is asking. But is there a difference in the process? No. If you are told to maximize or minimize something, the process is exactly the same. It means to take the derivative, set it equal to 0, solve for x. That's it. Okay, so let's get started. All right. So, number 1, find the dimensions of a rectangle with an area of 200 square feet that has the minimum perimeter. So right there, it's already telling us. It wants us to minimize perimeter. And it is also giving us another piece of information. It's telling us that the area is 200 square feet. So I will draw a small diagram really fast. I will draw my rectangle. Okay, yes, that's my rectangle. Okay, where I'll put the width as x and the length as y. And there are some things we know about a rectangle. 1, the perimeter. Perimeter of a rectangle is 2x plus 2y, or 2 length plus 2 width. And then area of a rectangle is given as length times width, x times y. Okay, so from the problem above, it tells us to minimize the perimeter. So our job is to minimize this perimeter function. But in order to do so, we need to make it all in terms of one single variable, which means you have 2 choices here. You can put this all in terms of x, or you can put this all in terms of y, which means I could make a substitution for x, or I can make a substitution for y. Well, what we are normally used to is just putting the equation all in terms of x. So for now, our goal is to replace this y value. Okay, so that's what we're going to do. So I'll call this step 1. we need to make a substitution for y. We need to make a substitution for y. And to do so, we will use the other piece of information that's given above. We know that the area of this rectangle is 200 square feet. So that's what we're going to do here. First, I'll rewrite the area equation. Area equals x times y. But now we know that area is 200 square feet. And now all we have to do for this equation is solve for y. So divide by x, and I get 200 over x equals y. This is my substitution. So now, what I'm going to do with that is take it and plug it in for that y value. Doing so will put perimeter all in terms of x. So that's what we're going to do. Okay, so let's go to a step 2. We will plug y into perimeter. So I will rewrite the perimeter equation. Perimeter is 2x plus 2y. And then I will now plug in the substitution for y, which is right above. Y is now 200 over x. So that's what I'm plugging in, which means I'll have 2 times 200 over x, which then will give me p equals 2x plus 400, and I'm going to rewrite this by flipping the x up. 400x to the negative 1. This is our new perimeter equation, all in terms of the same variable, and that variable is x. That's it. So this is the new perimeter equation. Okay. How am I using my space? Pretty good. I can come over here to the right. I'll make step 3 up here. Step 3. Since we have the perimeter equation all in terms of one variable, we now want to optimize perimeter. Which means that I will rewrite our new perimeter equation. P equals 2x plus 400x to the negative 1. Let me make sure that's right. Yes. Which means that now, since it's in terms of one variable, we can now take the derivative with respect to x. And if I optimize this, we will get p prime equals 2 minus 400x to the negative 2. Now remember, after you maximize or minimize something, you set the derivative equal to 0, which means we'll have 2 minus 400 x to the negative 2 equal to 0. Now let's solve for x. I'll get 200 equals 400 over x squared. I just added 400 to the right and flipped x down to the denominator. Now multiply both sides by x squared. I get 2x squared equals 400. Divide by 2. X squared equals 200. And then square root both sides. Whatever that is. 10 square root of 2. So I get x equals plus or minus 10 square root 2. Okay, well, since we are talking about length here, we can only keep the positive one. So this means my answer for x is 10 square root of 2 feet. Okay. The last thing to solve for is y. So if we found x, this means we can find y. Well, what's beautiful about that is that we already made an equation for y. That equation is right there. Y equals 200 over x. So all we have to do is plug in the x value we found, and we find y. So I'll make this step 4. Find y. So again, I'll rewrite the equation. Y is equal to 200 over x. And we know that x is 10 square root of 2. So I get 200 over 10 square root of 2. Plug that into my calculator. And 200 over 10 square root 2 is 14.14. Or again, 10 square root 2 feet. Okay, well, we need to answer this question because it says, find the dimensions of a rectangle with an area of 200 square feet that has the minimum perimeter. So our goal here is to find the dimensions. So that's going to be step 5, which I'll put right down here. Step 5. Dimensions. In order to minimize the perimeter, the dimensions of this rectangle need to be 10 square root 2 feet by 10 square root 2 feet. That's it. Or if you put it in decimal notation, it would be 14.14 feet by 14.14 feet. So this is what it wants. Okay, which means that if we're going to optimize this rectangle, it becomes a square, meaning the sides are the same. All right, so optimizing rectangle becomes a square because nobody likes rectangles. Trust me, nobody likes rectangles. Okay, let's move on. Okay, that's optimization. Number 2, a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So there it is. It's really telling us what we need to do. We need to find the largest area, which means we need to maximize area. Okay, so let's draw our diagram. It's cool that I have colors on here, right? So there's my river. And then here's going to be my rectangular field that borders the river. Okay. And again, I'll label this as X and that as Y. Okay. So for this fence, I'll even label this one X. We're going to have to find the perimeter equation for it. So for this fence, the perimeter is going to be 2x plus y. The reason it's not 2x plus 2y is because we don't need a fence on the side of the river. So that's why it's 2x plus y. And since this is a rectangle still, well, the area, no matter what, is still x times y. Okay, and now by the problem, our goal is to maximize the area. So again, you have your choices. You can make this all in terms of x, or you can make this all in terms of y. Well, what we like the best is what we're used to. We're going to make this all in terms of x, which means we need to make another substitution for y. So we have to replace that y in the area equation. Okay, so this will be step 1. Make a sub for y. Which means this time, we're going to have to rearrange the perimeter equation. P equals 2x plus y. P equals 2x plus y. Well, what do we plug in for perimeter? What else does the problem give? Oops, sorry. We are given that the farmer has 2,400 feet of fencing. 2,400 feet of fencing. So that's going to be the perimeter, because that's the most material this farmer can use. So that's what we're going to plug in for P. So P, nope, sorry. So 2,400 is going to equal 2x plus y. Now all we have to do is solve for y. So I'll get 2,400 minus 2x equals y. There's our sub. And again, what we're going to do with that sub is plug it in for that y value in area. Doing so, we'll put area all in terms of x. Okay, so that's 2. Let's make a step 2. Plug y into area. So area was given as x times y, which means that we will now have area equals x times 2400 minus 2x, which is the new replacement for y, right? What did I do? A different color last time? Sure. 2400 minus 2x. There's the sub. Okay. And then distribute the x, and area equals 2400x minus 2x squared. There is the new area equation, all in terms of x. Okay. And then 3, I'll come over here to make the most of my space. 3 optimize area. Optimize area, which means our new area equation is, where is it? 2400x minus 2x squared. (2400x minus 2x squared). Now take the derivative. A prime is going to be 2400 minus 4x. Then after you optimize something, you minimize something, you maximize something, you set the derivative equal to 0. So 2400 minus 4x will give me 2400 equal to 4x. Divide by 4, and x should be 600. And that is 600, what are we in feet? Okay, so x is 600 feet. So in order to optimize this area, in order to maximize the area of this rectangular field, the length of x has to be 600 feet, which means all we have to do now is find y, which again, we made a substitution for y. We made an equation for y. Y equals 2400 minus 2x. So all we have to do is take 600 and plug it in for that x. So 4, find y. And the equation for y is 2400 minus 2x. Let me double check. Yes. Now plug in 600, and y equals 2400 minus 2 times 600, which means y is going to be 1,200 feet. So in order to maximize this area, x has to be 600 and y has to be 1,200. This means that my dimensions, 5, it's going to be 600 feet by 1,200 feet. That's it. So those two were warm-ups, and those two problems show you how to work optimization. You have to know the formulas and know what you're maximizing or minimizing, know what you're optimizing, and then you have to put it in terms of one variable, which means you're always going to have to make a substitution for what variable you want. And once you do that, you plug it in, you get it all in terms of the one variable, take the derivative, solve for x, solve for y, whatever variable you're given, find the other variable, boom, that's it. So that's how optimization works. Okay, let's keep going. Three, a cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. So the equation for the surface area of a cylinder, because the cylinder is the can, will be A equals 2 pi r squared plus 2 pi rh. So that's the formula we will be using. That is the formula we are meant to minimize, okay? That's what we need to minimize. But let's take a peek at it real fast. So this is why we make substitutions, right? So let's say Let's say I was to minimize the surface area right now. We would run into an issue because of this RH. If you product ruled this, you would get R plus H prime R, which means we don't need an H prime for this. The height is not changing at a constant rate. So if we were to take the derivative, it would become an implicit derivative because of this R times H, and we would get a variable we don't need. We would get H prime. Do we need an H prime? No. Which brings me to the next steps of, well, we have to make a substitution for that H. And that's where this formula comes in. V equals pi r squared H. Okay, so this is what we want to minimize, okay? All right, so we want to hold 1 liter of oil, and the volume of the cylinder is given by V equals pi r squared H. Also given here is that 1 liter is 1,000 cubic centimeters. No idea, or maybe a little idea of why it wants us to convert this problem into cubic centimeters. Yes, volume is given by cubic centimeters and also by liters, right? But for this problem, just to work nicer, we're going to convert it to 1,000 cubic centimeters. So our first step is to make a substitution for that H. Okay, so that is the first step. So step 1. Make a substitution for h. And what we're going to use is that formula above for volume. Volume equals pi r squared h. Well, we know that we want this can to hold, what is it, a liter of oil, right? We want this can to hold a liter of oil, a liter of cola, okay? So this means that we want this can to hold 1,000 cubic centimeters of oil. So we plug in the 1,000 for the 1 liter, okay? So now, all we have to do is solve for h, which means divide by pi r squared, divide by pi r squared, which means that h is equal to pi r 1,000 over pi r squared is equal to h. And again, this is our sub. All right. And again, the reason it's, I can explain the reason when we get towards the end, but the reason we converted from a liter to 1,000 cubic centimeters is in the calculations. So when we get there, I'll try to remember to explain it. Because you can leave it as 1 liter, but that'll throw everything else off. Okay, so this means that we will take our sub and plug it in for that h value into surface area. Okay, that's where we'll plug it in. Okay, so 2. Plug h into surface area. And let me rewrite that surface area equation. So that's given by A equals 2 pi r squared plus 2 pi r h, not to the h, 2 pi r h. Okay, and now we're going to plug in that substitution. A equals 2 pi r squared plus 2 pi r times that substitution of 1,000 over pi r squared. Okay, so we are making a substitution for h, and cleaning up some more, you get A equals 2 pi r squared plus, and what happens here is that this pi and that pi cancel, this r and that r squared cancel, and what you're left with is 2,000 r to the negative 1. That's it. This is our new surface area equation, all in terms of the same variable, and that variable happens to be r. Okay, perfect. I'll just keep working down. Okay, which means that if we have surface area all in terms of the same variable, that means step 3, we are ready to go. We are ready to optimize surface area. Oops. Which means take the derivative. And I'll just do that now. I'm going to take the derivative of what we're looking at above right there. So, and of course, the derivative is going to be with respect to r, the variable that's there. So the derivative is going to be a prime equal to 4 pi r minus 2000 r to the negative 2. 2000 r to the negative 2. Okay. Now, after you optimize something, you set it equal to 0, and we get 4 pi r minus 2000 r to the negative 2 equal to 0. Let's go ahead and solve for r. So I get 4 pi r equal to 2000 over r squared. Then cross multiply, right? And you get 4 pi r cubed equal to 2000. Now, divide by 4 pi, divide by 4 pi, and you get r cubed equals, what's that? 500 over pi. Because 2000 over 4 is 500. Okay. Then, what you're going to do to both sides to solve for r is cube root. We get r is equal to, let me see, second cube root 500 over pi. I get to 2 decimal places 5.42. Oh, and by the way, this was in cubic centimeters. So this means that this becomes that r has to be 5.42 centimeters. Okay, excellent. Well, now here's why I get to explain we converted from 1 liter to 1,000 cubic centimeters. So if you left this as 1 liter, I believe that this would have become, so here's my what if moment, right? So if we did not convert, then this would have been, what is it? This still would have been 4 pi r equal to 2 over r squared, which would have gave me 4 pi r cubed equal to 2, and r cubed would have been 2 over 4 pi, where then you would cube root that, and r would be, and remember now, since you did not convert, this is still in liters. So if I did that, second cube root 2 over 4 pi, you get 0.542 liters. Now, for cans, well, for the surface area of the can, we don't want to give that to people in liters because we don't do measurements of can in liters. So now all this makes sense is because we can't say, well, the radius has to be 0.542 liters. Like, we don't measure that in liters. You don't measure surface area like that. So The reason we do that conversion in the beginning is because we need to have it in actual terms of length. And liters doesn't give me length. Liters gives me volume. So if you happen to multiply this number by 10, we get 5.42 centimeters. So that's why we make the conversion in the very beginning, because we're taking a volume and we're actually going to put it into a length later on. So that was the what if moment. If you were wondering why we converted from 1 liter to 1,000 cubic meters. And the reason is to put it in terms of length once we get to the final answer. Okay, there you go. But okay, well, this problem is asking for the dimensions that will minimize the cost. So if we know the radius, this means we need to find the height of the can. So we need to find the height of the can. So I'll put it right here. I'm going to say step 4. Find height. And we made an equation for that. Height was 1,000 over pi r squared. Is that right? Where are you? Where are you? Height is 1,000 over pi r squared. Okay. Well, we know that r is 5.42. So we plug that in. So I get h equals 1,000 over pi times 5.42 centimeters squared. Oh, and this is, now I have to put units in to make this proper, because this is still 1,000 cubic centimeters. Okay. Calculate that. And I do 1,000 over pi times 5.42 squared. And I get 10.84 centimeters. So 5, put it together. Dimensions. Radius has to be 5.42 centimeters. And height has to be basically double that, 10.84 centimeters. There it is. Beautiful. Okay, excellent. So again, you see how optimization works. We given the information, we rearrange, we make a substitution, we plug it into the other one, we optimize it, we solve for the variable. Once we find that variable, we find the other variable. All right, so for this can to hold 1 liter of oil, the radius needs to be 5.42 centimeters, and the height of the can must be 10.84 centimeters. Okay, perfect. All right. I didn't even draw a diagram for that. Didn't need one, but we could have used one, right? Should I even try and draw a can? Let's see. Don't be mad at my can skills. Close enough. Let's try that. There you go. There we go. All right, cool. All right, example 4. I'll take a break for a real quick second. Okay. A box with an open top is to be constructed from a square piece of cardboard, 3 feet wide, by cutting out a square from each of the 4 corners and bending up the sides. Find the largest volume that such a box can have. All right, so we're looking for the largest volume. So our job is to maximize volume. Our goal is to take the volume of a cube and maximize it. Okay, so this one I think we need a diagram for. So first we know that our square piece of cardboard is 3 feet wide. So that's what I'll start with. Ooh, this does shapes. Let's see. Oh, ink to shape. There we go. Let's see how this works. So first off, yeah, look at that. Beautiful. Okay, cool. So we know that my box is 3 feet by 3 feet. But then we are going to cut small corners out, square corners out from this box. Man, this is great. Okay, so what I'm going to do is cut square corners out. Okay, perfect. I do want to ink to shape that one. Whatever. Okay, so we do that. Okay, so we cut small square corners from each. So what I want to do now is label those cuts. Okay, so since we're cutting these corners out, here's what I'm left with. So I'm going to go to the next diagram. This is what I'm left with. I wonder if it'll draw this to shape. Let's see. If not, I gotta do it better. Nope, it didn't. Okay. Ooh, what if I did rectangle? Let's see, rectangle over rectangle. There we go, that's better. Not perfect, but it's good. Okay, so this means that for these small corners, I will label them, and the labels on the corners we cut, this will be X, and that will be X. And then this means that this will be the inside, the base will be Y. Oops. Y, this is Y, that's Y, and that's Y. So the inside squares the base of the box, which will be labeled Y, and then everything else is X. This is X, and that's X. Maybe I should use different colors. Huh? Oops, nope, didn't want to do that. Stop it. Let's see. Let's do my relabeling since this is working really well right now. This is Y. that's y, that's y, that's y. Okay. And I'm going to get rid of that x too, which means it's probably going to erase everything. Oh, there we go. Okay. So I want to make this labeling as clear as possible. So here's what I'm going to do. This is x, that's y, this is x. There we go. Okay. So our goal is to maximize volume. So what we did is that we cut 4 corners out and we're going to bend up the sides. Okay, so this means I need one more diagram. Okay, it's going to be my 3D diagram, so bear with me. Okay, all right. Wonder how well I can do this. Let's see. So the next one. Into shape. No, you don't want to? There we go. Okay. All right. So here's my box. And then maybe I need something on the inside too. There we go. So if I label this, when you fold it up, the base remains y. So what we know is that this is y, and that is y. And when you fold it up, the height of the box is x. Hey, look at that. That's not bad. Pretty. Okay, so now I'm done with my diagram, sorry. So our job is to maximize the volume. Okay, so we know that we are given volume as length times width times height, where here the length of my box is y, the width of my box is y, and the height of the box is x. So this means that volume becomes xy squared. So this means that volume is given as xy squared. And this is the one that we need to maximize. Oh, now it's just inking to shape everything. I'm going to turn it off. Okay. So if we want to maximize this function, well, we have to do what we've been doing for all the other problems. Make a substitution for y. So our goal is to get rid, our goal is to get rid of this y. So we have to make a substitution for that y. Okay. Change colors and everything. My goodness, stop it. Okay. Well, in order to make a substitution for that y, we need another piece of information. And that information says that our box is 3 feet wide. Well, now, since we cut our box, we see that looking at the third diagram I drew, that the width of this box is given as x plus y plus x. So with that being said, we know that my width, let's see, what's going to be the best way to write this? Oh yeah, so width is given by x plus y plus x. So width is given by 2x plus y. But now we know that width is given by 3 feet. So my width is 3 equals 2x plus y. Okay. So we have the equations we need. Okay. So now let's put these into steps again. So I'm going to say 1. Make a sub for y. And we are using the width equation. Width equals 2x plus y. We know that 3 equals 2x plus y. Therefore, 3 minus 2x equals y. Here's my sub, which means step 2, plug y into volume. So we know that volume is given right now by xy squared, which is right there. Volume is given by xy squared. So all we have to do now is plug volume in for x times my new y value of 3 minus 2x squared. Okay, so there is our new volume equation, which means we are now ready to take the derivative, which will be right here. Step 3. Optimize volume. So given V equals, what do I have? X times 3 minus 2x squared. Let me just double check. X times 3 minus 2x squared. Okay. Now let's take the derivative. But if we take the derivative, this is going to use product rule. So that's F and that's G. So F is X. G is 3 minus 2x squared. F prime is 1. G prime is 2 times 3 minus 2x times negative 2. So clean G prime up and you get negative 4 times 3 minus 2x. Okay, which means we're ready to come back to the derivative. V prime is F prime G. 3 minus 2x squared plus G prime F. That's going to be negative 4x times 3 minus 2x. And you get V prime is equal to 3 minus 2x squared minus 4x times 3 minus 2x. Okay, let's make this look pretty. And I will factor out a 3 minus 2x. And that'll leave me with 3 minus 2x minus 4x. Therefore, v prime is 3 minus 2x times negative 6x plus 3, or 3 minus 6x, whichever you like. Yes, you can factor more out, but we don't have to. We can now set v prime equal to 0, which means you get 3 minus 2x times negative 6x plus 3 equal to 0. Set both of these equal to 0, and you should get x equals 3/2 and x equals negative, not negative, x equals 1/2. And these should be in feet. Okay. Whew. Almost there. We now have x. We need to find y. Well, now we have two x values. So we have to see which one's going to work. So that's going to be step 4. Step 4. Find y. Given the equation, y equals (3 minus 2x). So let's try our first x value. At x equals 3/2, we get y equals 3 minus 2 times 3/2. This gives me 3 minus 3, which gives me 0. 0 feet. Can we use 0 feet to complete my box? No. So this means 3/2 is out. Now, let's try it at 1/2. Y equals 3 minus 2 times 1/2 gives me 3 minus 1, which gives me 2 feet. Can we use this? That is, yes. So this means that if we're going to optimize the volume of this box, y must be 2 feet. Okay. Is there one more thing to answer? What's it say? This says, find the largest volume that such a box can have. So now we're going to take x and y and plug it into volume. So here's number 5. Volume equals x, y squared. So we get v equals 1/2 foot times 2 foot squared. And if x is 1/2 and y is 2, this means that the maximum volume this box can have is, well, that's 4 times 1/2. So the maximum volume this box can have is 2 cubic feet. There it is. Not bad. Not bad. Okay, perfect. One more left. Okay. Last one. The sum of two positive numbers is 16. What is the smallest possible value of the sum of their squares? So what is the smallest possible value of their sum of squares? Our job is to minimize the sum of their squares. So let's see. So let's start off with the first piece of information given. The sum of two positive numbers is 16. Well, I bet it's 8 and 8. Just a hunch. Okay, so this means that I have x plus y equals 16. So the sum of two positive numbers is 16. So now we use that information. Now, what is the smallest possible value of the sum of their squares? The sum of their squares. This means that the sum of their squares would be x squared plus y squared equals some number. Let's go with z. Why not? And our job is to minimize this one. Minimize. Which means make a substitution for y. Well, let's change it up a bit. We've been doing substitutions for y all day. Let's make a sub for x. So let's start with that. Let's change it up. So 1. Make a sub for x. And of course, we use x plus y equal to 16. Solve for x. X equals 16 minus y. There's my sub. Now, 2. Plug x into, what do we call that? Sum of squares? Yeah. Into sum of squares. Okay. So my sum of squares above is given as x squared plus y squared equal to some number z. Now we're actually making a substitution for x this time. So this becomes what did I do? Okay, yeah. So this becomes 16 minus y squared plus y squared equal to z. This is our new sum of squares formula, which means we are ready to optimize. So 3. Optimize sum of squares. Okay. So I'm going to take the derivative of the formula above with respect to y. Let me rewrite it. So 16 minus y squared plus y squared equal to z. Now, if I take the derivative with respect to y, I must chain rule the first part. So this becomes 2 times 16 minus y times -1 plus 2y equal to z prime. Okay. And then this becomes -2 times 16 minus y plus 2y equal to z prime. Let's go ahead and clean this up. And I get -32 plus 2y plus 2y equal to z prime, which means we get 4y minus 32 equals z prime. Now, it's nice and cleaned up. Take z prime, and set it equal to 0. 4y minus 32 equals 0. 4y equals 32. And y equals 8. What did I tell you? This means that if y equals 8, x must also equal 8. So, move on to step 4. Find x. And we know that x is given by 16 minus y, which means x equals 16 minus 8, which means x is also 8. Done. So the sum of two positive numbers is 16. What is the smallest possible value of the sum of their squares? Oh, so we're not done. So 5. Find sum of squares, which means you would have, well, 8 squared plus 8 squared equal to z. And the smallest possible value for the sum of their squares is, whoops, that's 64 plus 64, so that's 128 equals z. There it is. Now we're done. So 128 is the smallest possible value for the sum of their squares. Woo! And that is optimization. Which means that test 3 should be coming now. Okay. So again, for optimization, know what formula to use, know what substitution to make, plug that substitution in. Once you get your formula all in terms of one variable, then optimize it, solve for the variable, solve for the other variable, done. Okay, that's it.